In the previous module, we looked at Euler's method and used Euler's method to obtain an approximate function, piecewise linear function, to the exact function. One thing that we did in there was we talked about what was the end behavior of the unknown function or of the exact function, and we talked about end behavior, stabilization value, that sort of thing. And here in this module on limits, we are going to work on clarifying that idea of a limit a little bit more. And so we're going to apply a limiting process to determine the value of the limit. That's what we're going to do in this video. And then in future videos, we will evaluate limits of unknown functions at infinity, of known functions at a point, use limit laws, and then throughout the entire module, really, what we want to do is determine the value of a limit algebraically, graphically, and numerically through a table. Okay, so one problem in Module 1A that we encountered was we had a hot cup of coffee that was at 180 degrees Fahrenheit and was cooling in a room that was at room temperature, so 70 degrees Fahrenheit, according to Newton's law of cooling. And we talked about writing a difference or a rate of change equation, and if you actually solve that directly for temperature, you obtain this solution. 70 plus 110 e to the minus 0.8 or 0.08181 times t. Okay, so what we want to know is what is the temperature at which a coffee stabilizes? What is the as you increase time without bound? What is the temperature that the coffee approaches? Okay, in a couple problems in web work, we use the term steady state. Same idea. What does it approach in the long run? What does it approach after a long time? Okay. We also mentioned we want to come to recognize what the term limit means, but also be able to represent it in a variety of ways, one of which was graphically. So if we look at the temperature as a function of time, we can obtain this graph. So temperature is on the vertical axis and time is on the horizontal axis. So we see it initially starts at 110 degrees Fahrenheit and decreases over time, and eventually we see from based on the graph it looks to approach 70 degrees. Okay, so we say that as t approaches infinity, so it increases without bound, then temperature approaches 70 degrees. Okay, but this may or may not be true, so let's see if we can obtain the same value through a variety of other ways. Okay, so another way that we mentioned was numerically, which we will do through the use of a table. And the table has been constructed for this function. So the independent variable time is in this first column, and then the dependent variable temperature, capital T, is in the second column. And if we look at almost the entire table here, we see that as we increase time is going up by 10 minutes. We see that it's going down, and it's leveling off. It looks to be around 70, and in fact, when we get down to 200, when time is 200 minutes, it is nearly at 70 degrees. Okay, so again, we say that as time approaches infinity, temperature approaches 70. Now, keep in mind that infinity is a concept. It's not a number. So we can't actually attain this value, but we can get ever closer towards it. Same thing with the temperature. We cannot say that the temperature is 70. It will never be exactly 70, but it will get ever closer to 70. Okay, so it approaches, but it does not attain. And then the last way is through the use of algebra. And really what we want to think about is with this function, what is its end behavior? Okay, and really what we want to think about in this function is, well, the 70 really doesn't play any role. Okay, so when time gets arbitrarily large, 70 will still be 70. But what happens to this chunk over time? Well, we know that the basic exponential function, if this was a positive constant, would approach infinity as time increased. However, this is a negative, so it's a horizontal reflection, and so this component, as time increases, as time increases, e to the negative 0.08181 times t, that will actually approach 0. Okay, meaning as a whole that as time increases, temperature is going to approach 70. Remember, the 70 didn't change over time, and then this entire value over time will actually approach 0. Okay, or we can just say, doing the arithmetic, 70. Okay, again, same way, or same answer, different way. So 70 degrees Fahrenheit, we actually call the limit or stabilization value. We could also again say that 70 is the stable set, or the stable value, or steady state of the function. The limit or stabilization value. So again, and we emphasized this before, but as time increases without bound positively, or negatively if it approached negative infinity, we say that time approaches but does not ever equal 70. Okay, and again, you can't actually say time is infinity. It gets larger and larger and larger, but does not ever reach that value. And so, condensing all this mathematically, we can say the limit as t approaches infinity, as time increases without bound, of capital T of temperature is equal to 70. Okay, just condensing that notation a little bit. So, basic idea of limiting process: we can represent a limit algebraically, which we just showed, numerically through a table, or graphically by making a graph of the function. And so in the next video we'll look at infinite limits, and then eventually we'll talk about limits at a point, and then finally the limit laws. Stay tuned.